So, good afternoon again, everyone. So today we should continue what we have done last week. Yeah, last week we have looked at uh, the high-level design and high-level design concept. Yeah, how we design at the design abstraction that is higher than RTL design. So we actually have looked at this. Yeah, we have the algorithm and we convert or translate the algorithm into the DFG, and we have done the scheduling and allocation. Yep. But in previous or last week example, we haven't applied any constraint to our design yet. So today we will look at that, how to apply the constraint to the design. And last week we also have looked at the how to do the scheduling, how to do allocation, and from that we can derive the RTL code, and we actually have derived the data path unit for the design. So we have looked at the this example 6.3, where we have derived the DFG, yeah, based on the equation given, or we can say that this is the algorithm. Yeah. So, and this is the schedule and also the resource allocation for our design. Yeah, based on this DFG, we can create the schedule like this. So we have S0 until S3 here, right? So I have explained to you how to derive this last week. And from this, we can derive the RTL code. Yeah, and we can see that here, based on the question, yeah, as to uh, design the data bus that allows for concurrent computation of three additions. So we can have three up to three adders, yeah, in our design. So this is clearly demonstrate that. So we can see that in any uh, single cycle, in any cycle here, we can see that the maximum number of adder is three, right? So we can see that here as one, we have three adder, three add operations that will be executed at the same time in the same at the same cycle, means that we need three adders here, right? S2, we only use one adder. So because we have three, then one adder is no problem for us. So we can use this, adder number one for this operation. And actually you can use uh, adder number two or adder number three, because all are available in this cycle, S2 cycle. In this example, I use adder number one, right? So if you design your own circuit later on, you can actually use any of the adder that you have. In this case, we have three adders, so any adders you can use, right? And S3, we don't have any add operation, so we don't use adder. We only use multiplier. And S2, we have one multiplication here. Okay, and everything here we can easily derive the RTL code, and also from the RTL code we can now derive the um, data path, yeah, from that. And also I also have explained to you, demonstrate to you how to derive this last week, right? Okay, so we have the design here, and And last week we have looked at, yeah, this is our design last week, right? And this is actually same as this one, right? Where we have 4 to 1 marks here. This art, we have register 4 registers, 1 multiplier, 3 adders, right? And the connection, how to create the connection, this is actually based on the RTL code that we have, right? So this is the RTL code. So I have demonstrate to you how to do that. And also we have uh, the Verilog code, yeah, to describe this circuit already last week, right? And this is the code to describe the circuit. So this again shows how we could, yeah, to describe our circuit if we have the circuit like this. So of course the first thing you need to figure out is what are the inputs outputs that we have, the port, right? So here, although in the notes there is no label, for example here SEL-R1, there's no label. So in the actual design you need to have that, because yeah, this is multiplexer, you need to have the control input, right? Control input. And of course when SEL-R1 equal to 0 0, so what is value? Yeah, in this case, if 0 0, A will go to R1. If 0 1, the output from the multiplier will go to R1. If 1 0, the output from the adder number 1 will go to R1. And of course the SEL-R1 will be 2-bit, yeah, because this is 4 to 1 multiplexer, and we have others as well here. And we have the load signal, yeah, to load the data into the register. So we name it LD1 for R1, LD2 for R2, and so on. And of course here there are other signals that you need to have, for example the clock, yeah, and the reset. But that one is a common signal, so no need to have it here, right, to make it simple, okay? But in your code here you need to have that, right, such that you can describe the things. So this is a R1 here with the multiplexer, right? So if you look at the code, this is positive edge triggered clock, and we have active high reset for R1. And of course if reset equal to 1, because we have post edge here, then R1, yeah, the output of the register R1 is equal to 0. And observe that I use the non-blocking assignment here because we are describing the sequential circuit. Okay, and if reset is not active, so we will look at the next signal, which is LD1, whether it is active or not. So if it is not active, means that the value of R1 will remain the same, right? But if it is active, we will look at the input here, and this input here is again depend on SEL-R1. So we can see that if LD1 equal to 1, now we will look at this signal, right, where If it is equal to 0, 0, so the input to the register will be A. And of course, the output R1 will be equal to A. If 0, 1, it will be equal to MUL. If 1, 0, it will be ADD1. Where is ADD1? This is ADD1, right? And again, you need to remember that if you use case statement, make sure that you have all the combinations, possible combinations of the input. So because we have two SEL, yeah, SEL, we have to bit, meaning that we need to have 4 possible combinations. So we have 0, 0, 0, 1, 1, 0, and actually 1, 1 here. And 1, 1, you can put it default, or you can write it 1, 1. And if 1, 1, R1 is don't care, or you can put it a high impedance Z, right? Same thing. R2 is actually looks the same as R1 because we have 4 to 1 multiplexer before we go to R2, right? So the structure must be the same, except that the label, the signal is different, and the name of the signal is different, and of course the input here. But you can see that here the structure is actually the same, right? So this is R2. R3 is even more easier as compared to R1 and R2, where we don't have we have multiplexer, but the multiplexer is 2 to 1, so we can use only instead of case statement, you can use if else statement, right? So if SEL R3 equal to 1, so you have R3 equal to C, else if equal to 0, it's equal to E, right? Based on this. And for R4, this is actually similar to R3, right? Because you have 2 to 1 multiplexer here, then you can have this. Okay, so next we look at the arithmetic or the processing circuit. The first one is the multiplexer, and the multiplexer we have not multiplexer, multiplier. So for this multiplier, we have the multiplexer right before the for both of the input here. So if you have multiplexer, means that you can have in this case 4 possible combinations for the input, right? Whether 1, 1, 1, 0, or 0, 1, or 0, 0, right? So you can, if that is the case, so you can use the case statement as well. So this is the skill of writing the code. So if you want to combine this multiplexer with the multiplier, right? So this is how you code it. But if you want to create different block using different always block, you can do that as well. But of course, this signal, this wire, you need to have a label. You need to name it, right? But in this case, no need to name it because we describe based on the input here and the output here. Okay, so I think this is the best way to describe this. Yeah, but again, this is depend on how you want to do it, right? There is nothing wrong if you make or create this separately. Okay, but if you want to combine like this, so of course we need to combine the SEL M1 and SEL M2 to be one signal such that we can use case statement, right? So to do that, you need to use the concatenation, right? This is concatenation as ALM1 and SELM2, such that if 0, 0, so we can have, yeah, look at this. If 0, 0, what is the what is the operation. So the 0 0, if 0 0 must be, right, if both 0 must be, the output here MUL is equal to this, which is R3, and multiply by this one, which is R2. So that is why we have R3 multiply R2 here, if 0 0. But if 1 0, so we can have R3 again, because if 0 1, sorry, if 0 1, so this is still R3, and if 1 here means that this is R1. If 1 0 1 means that this is R4 multiplied by R2, and if 1 1 must be R4 multiplied by R1. Yeah, so that is the multiplier. So for the adder, this one is we have only one multiplexer here, so you can create like this. Yeah, if SELA equal to 1, so the output here will be equal to R1 plus R2, and if it is equal to 0, means that R1 plus this one, which is R3, right? And for adder number 2 and number 3 is easy. We don't have any multiplexer here, so it is straightforward, where add 2 is, yeah, definitely R1 plus R3, and add 3 is definitely R3 plus R4. That's why we have this. Okay, so it is directly translated or represent this circuit. Actually, Verilog HDL is very good hardware description language, that it is very structured, and it's directly represent what we have and the hardware that we have, right? You can see here. Okay, so that is how we create this data path. So next step, yeah, and again, the question does not ask you to create a code, yeah, but this one I just show to you, yeah, how to write the code for that. So this question actually asks you to create the data path, right, until this only. Okay, but in the assignment later on, I will ask you to have the code, and of course to uh, to provide the simulation result. So that is why I demonstrate to you how to do that. Okay, such that you know how to do. Okay, so that that is not finished yet, because to have a complete design, yeah, not only the U that you need to have, but you need to have the controller, or the control unit. So how to design the control unit? It is again will be based on the RTL code here, because in the RTL code it defined clearly what is the operation, what are the operations that we need to do in each cycle. For example, this cycle we want to do this we want to do this, S2 we want to do this, and S3 we want to do this. So if this is the case, means that for each cycle we need to activate the correct signals. Yeah, for example, if we want to load data from here A to R1, so LD1 must be 1, LD2 must be 1, LD3 must be 1, LD4 must be 1, and also all this signal that control whether which one will go to R1, which one will go to R2, must be activated correctly. All right, so for example, if we want A to be in R1, so the signal here will be 0 0, right? So that is the uh, the things, and we can create that, yeah, sequence of operation by using the finite state machine, FSM. Okay, we have learned how to build the finite state machine, and this we can actually create the finite state machine to uh, to do that. So before we can have the control unit, yeah, the CU, so we need the what we call the RTL control sequence. Yeah, this is called RTL control sequence, RTL, or in short RTL, RTLCS table, right? That will define what is the signal that what are the signals that need to be activated in S0, in S1, in S2, and S3, right? So now we want to create the CU, the control unit for this. Okay, so what we want to do is we want to create the controller. And this controller is, of course, the finite state machine. So make it smaller here. Okay, where this is the state register. And the output for this will be all of these control signals, right? Where we have this LD1, we have LD2, we have LD3, we have LD4, we have 2-bit SEL R1, we have also 2-bit SEL R2, we have SEL R3, we have SEL R4, we have SEL M1, and SEL M2, and the last one is SEL A, right? There are a lot of signals that we need to generate in order to get all this operation done. And of course, here we need to have the feedback, and this is the output logic. And this is the next state logic, right? So in this case, we don't have any input, yeah, to make this finite state machine to change the state, yeah, from state 0 to state 1, because here we can see that from state 0, next cycle we will automatically go to state S1, S2, and S3, right, without waiting for any input. Okay, but in the practical design, yeah, we actually normally have one input to trigger the operation. We call it the start signal, right? For example, this start will activate the operation. If this start is equal to 0, means that the operation, or this uh, finite state machine is, or this controller will be in the idle mode, yeah, do nothing. So if we draw the state diagram of of this operation, it will be something like this. We add another state as 0 where there is nothing happen, and if start equal to 0, we are here in state 0. But if start equal to 1, we go to the next state as 1, and this will go to the next one automatically as 2, as 3, and as 4. Right? We add another state, call it as you can call it as 0 or whatever, right? And this is the process, right? And after S4, it will go back to S0 to wait for another operation. Okay, so that will be the state diagram that we want to do actually. Okay, so that is why we have the start here, and we need to change this to, for example, if we need to have that, so this will be S2, this will be S3, this will be S4, and you can have another S0 here, right? You can have S0 here, and the RTL will be with condition, right? If you have start, you go to S1. Okay? And here is maybe we set on 0, right? This actually don't care, or you can put it on 0. Okay, so that is the things. And also when you look at this we have another signal, we call it Y done. So this signal is generated by the controller as well to tell the to tell or to give us the signal that the operation is done. So for example, if Y operation is finished, so this signal will be activated, and if X operation is finished or the result at R1 is ready, so X done is equal to 1. So this will be generated by the this as well, where you can have more output, X done and Y done, right? Something like this. Okay. Now, if we have this, we can create the Verilog code to represent this already, because we have the structure of this, and also we have the behavior of this based on this table, right? So let's do that. So here we create the new one. Okay, the control unit. And what is the name for this one? Yeah. Okay, let's use this name. Okay, so we have that. So we need to create the Verilog. Uh, the name is this. We have the clock signal. We have the start, reset. We have this. So it must be based on this. So let's have this here. Okay. So we have reset, start. So where is reset? Reset is here, and for the controller, we will use the negative edge clock. I will explain later on why we use negative edge. If you look at the before this, the data path, I use the positive edge clock, but for the controller here, I use the negative edge clock. Yeah. So this is clock, and of course you have reset, and you have the start signal. You have the all the LD, everything there, LD1, LD2, LD3, LD4, you have SEL R1, you have SEL, we use SEL R2 here, yeah. We have R8, SEL R3, we have SEL R4, and we have SEL M1, SEL M2, and we have SEL E, and we have the X done, Y done signal. X done, Y done. And I want to add one more signal. This is for debug purpose, such that in the simulation later on we can see this. Yeah, if you look at this in the simulation, you can see that we can see the state here: state 0, state 1, state 2, state 3, state 4, for example, right? So in order to do that, what you need to have is that because the state is this signal, all right, so we need to tap that signal to the output. So we name it state, right? So we can have state here, okay, and now we have the input. So maybe you can list all the 1-bit input. Clock, reset, the start, the 1-bit input. We don't have any 2-bit input, so that's it. We have the output. The output here, all of these are the output, so we can actually copy this, yeah, the 1-bit output. Here is 1 bit, SEL-R1, SEL-R2 are 2-bit. No, this one is 1 bit. Yes, 1 bit. SEL-R3, SEL-R4 is 1 bit. Yeah, 1 bit, 1 bit. M1, M2, SEL-A, all are 1 bit. So we can copy this. 1 bit. What about X done, Y done? 1 bit also. So this is 1 bit. And the last one, state. State. How many bit is the state? How many bit is the state? So we need to see, yeah, how many bits. So to determine that, we need to look at how many states that we have. So here we have 1, 2, 3, 4, 5 states. If we have 5 states, so the size of the flip-flops or the register must be 3 bits, right? Because if you have 2 bit, you can only represent up to 4 states. Now we have 5 states, so you need to have more than that. So if you have 3 bit, you can represent up to 8 states. Yeah, so this state is 3 bit. Of course, this one is 3 bit, and this one is 3 bit. Okay, so here should be done here, and we should have the output that are 2 bit, which is the SEL-R1 and SEL-R2. Both are 2 bit. Okay, and this output must be in rect data type, right? Rect data type, and you will have another one, which is the state, 3 bit. The state is 3 bit. Okay, that will be the output. Okay, and what else that we need to have? We must have these signals, so we can call this as next state signal, right? So we need to have that as well, and it is not input or output, so we just declare as this as right. State signal for this. Yeah, and we want to in order to make it easy to write the output later on, so it is better to group this to be one signal, right, where we will call this signal as control vector or CV. Okay, so this CV is not including x done and y done. Yeah, only this. How many bits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13-bit CV, or control vector. So we can use this control vector to assign the value later on, right? It's easier to do that. Now we define our state. We use parameter, and of course the size is 3-bit. So we have as 0, which is represent number 0, as 1 represent number 1, as 2 represent number 2, as 3 number 3, and the last one is as 4 number 4, right? So should be done for the declaration part. And now we want to describe this. So this is the state register, and we have the negative edge triggered clock. So let's say, okay, we want to have the state register here. So let's create that. So we have negative edge clock and positive edge reset. So if reset is active, so the output, which is the state must be equal to 0 or as 0, right? So when we reset, so the output here will be always as 0, right? The finite state machine, when we reset, we will be always at state as 0. So here we can say that this is as 0 when reset. And if not reset, the output state will be equal to this next state. So we have next state. So should be done for this state register. Now we want to describe the next state logic and the output logic. So we can combine that actually. Next state and output logic. Right. So now the sensitivity list will be this start and also this one, the state. All right, because the input for this is start and state, and the input for this is state. So we have start or state. Okay, and we can use case state. All right, if as 0, what we want to do? If as 0, we have we will look at the start and also what are the output here, the CV, right? So the CV will be the best way to represent this number is to use hexadecimal, right? So in hexadecimal, this is equal to because we have 12-bit, 13-bit, so we need to have 4-digit hexa. So this is in hexadecimal, or you can write this way, H, right? Hexadecimal, such that here we can write this. So if S0, the output CV is equal to 13-bit in hex 1, 2, 3, 4. All right. That is why we use hexadecimal. If you use binary, so you need to have 13 digit in order to describe this CV. So it is better to use hexadecimal in this case, yeah, because we have 13-bit quite big there. And we need to look at start signal, right? Based on this, if start equal to 1, then we go to S1, but if start equal to 0, we stay in S0. So what we do is we can have, if we have another one, right? The output Y done should be equal to 0, and X done should be equal to 0 in this. Yeah, so we need to have all the combination. So if start equal to 1, the next state should be equal to S1, right? Else next state should be equal to S0 according to our specification. So that will be what in S0. Easy, right? Now S1 begin. Again, in S1, CV should be equal to 13-bit in hexadecimal. We need to change this to hexa. So this should be 8. This should be 1. This should be E, right? So remember to change to hexadecimal from binary. So you need to group by 4-bit starting from the right hand side. Okay, so for example, in this case, you look at this here, you have here, and you have here. Okay, you can see that this is 1, this is E. So you will have 1 E, this is 1 8, 1 8 in hexadecimal. Okay, so in your case here should be 1 E 1 8, and in this case Y done and X done is equal to 0. And we need to no need to check for signal start, because it will automatically go to S2 after we finish S1, right? So we should have S2 here, and our N is here. Okay, this is for S1. So we have CV equal to this. This one should be equal to 0, and the next state should be S2. So we are in S2. If we are in S2, so here should be the same, right? So just copy and paste, but this one should be different. Now look at this. So here we have 1, this is B, 1B, this is 2, 1B, 2, 1, right? So we have 1, B, 2, 1, H, and let's do for the rest. For here we have 1, C, this is C, and this is 4, this is 4, 1C, 4, 4. Is it C or D? This is not C, this is D. 1D, 4, 4. 1, 1, 0, 1 is D. Yeah, C is 1, 1, 0, 0. Okay. The last one we have 1, 0, 8, 2. And this is, of course, hexadecimal number. This is 1, 0, 1, 0, 8, 2, H. Right, so that will be our output. So go to here. Here must be this 1B21. So we have 1B21, and the next state must be 2 S3, right? And we have S3, so we can just copy here, except that the value here is 1D44. Okay, 1D44, and in S3 here, so we should get the result for Y already, right? Based on this, here. Right, remember now here is S3 already, because we add another state, yeah, S0, so this will be S1, S2, S3. So Y done equal to 1 here. Okay, so in this case, Y done should be equal to 1. Next, we go to S4, right? And let's have the last one, S4, and this will be 1082. Now we have this equal to 1, x done equal to 1, yes. And we go back to S0. Okay, and remember that if we have 3-bit states, yeah, and now we haven't defined or described all the state yet, right? Although we don't have S5, S6, but in Verilog we have to have that. Yeah, so default we can have this. CV, we make it 0, or you can have don't care. Oh, and this is not B, right? This should be H. H. Don't care. And next state, S0 should be okay. You can have don't care, and don't care also, right? Doesn't matter. And case done for this. Now what you need to have is that you need to map, because the output here, our output is call LD1, not the CV. So you need to map the CV to the output, or connect, yeah, the CV to the output. So you can start with LD1. So you can use LD1 here. No need to use rack because we will use the data flow modeling. So no need to use rack. Okay. So we can use sign LD1 is equal to CV, what is that? CV, in this case, CV12. Okay, and many more. So maybe we can just copy. So we have LD2, CD11, CV11. We have LD3, CV number 10. We have LD4, CV9. We have SEL, SEL R1, bit number 1, right? Which is CV number 8. And we have another bit, bit number 0, connected to CV number 7. We have R2 connect to CV number 6. We have bit number R2, bit number 0, connect to CV number 5. We have at SEL next, must be based on this SEL R3, R4. Okay, so SEL R3 is CV number 4. SEL R4 is CV number 3. Then we have SEL M1, must be CV number 2. And we have SEL number 2, must be CV number 1. And the last one is SELA, must be CV number 0. Yeah, so all of the CV0 until CV12, yeah, we have the connection, and that should be done. Okay, so we have all the description here for the control unit, and we can save. Okay, and try to have this. Okay, we have 12 errors. So yeah, look at this: X done, Y done. On the left hand side of assignment must have a variable data type. What is that? That means that the declaration of X done and Y done is wrong, because we have this variable in the always block, yeah, but here we should have the rect data type. So maybe what we need to do is x done and y done should be another output where we have frac data type for that, then should be okay. Right, any other error? X done, x, okay, that's it. All right, so we have done that. There's no errors, only one warning, and this warning is okay because this is about the software setting, not the design. So the design is okay. So we have the CU already. Now we need to integrate. Yeah, we need to connect the CU and DU to be a complete design, right? So what we need to have is our design later on will looks like this. Where we have the CU and DU data path and control, and this CU will generate or provide the control signal to the DU, which is the LD1, LD2, until we have the last one. What is that? Here, SELA, SELA, and of course this one will provide the done signal, X done and Y done, right, to indicate that the process is finished. And we have the input start here, right, and we have the DU. You will need to have the input A, in our case is 8-bit, right? We have B, we have C, D, and E. Okay, so that is the input. Later on in our simulation, we want to see what is in R1, R2, R3, R4. So basically the output is actually in R1 and R2, right, based on the design, 8-bit. But if you want to see the content of R3, R4, you can do that also, such that if anything happen, for example, if we verify the design, we test our design, we get the wrong result later on. So maybe the information that in R3 and R4 is useful. So in the simulation, it is better to include that as well. But the things that we want to create will be looks like this later on. Okay, so yeah, of course we need to integrate these two together to do that. Okay, any questions so far before we combine this CU and DU and see the simulation result?